Imagine that we give you the following question. We'll give you an integer n and we will want you to identify all prime numbers that are less than or equal to n. So for example, if we gave you the number 100 and said, can you identify all prime numbers that are less than or equal to 100? So the method that we will highlight is a very simple but a very elegant method known as the sieve of Eratosthenes. So we're going to outline the sort of sieve of Eratosthenes in the form of an algorithm. So that's the way we will sort of outline the procedure to actually find all primes less than or equal to some integer n. So that's our problem statement. So let's go ahead and write it out. That is to find all primes that are less than or equal to n, where n is an integer. So the first step is to list all integers, from 2 to n. So that's the first step. The second step is a bit of a sort of initialization step where we set p is a parameter, we set p to be equal to 2. We're choosing p because p also denotes a prime. So we set p equal to 2 and 2 is the smallest prime. So it's the smallest prime number is 2, so we set p equal to 2. Then what we do is we need to identify all multiples of p and then go ahead and delete all multiples of p and then delete all multiples of p. Now do note that the number p itself should not be deleted. Now that's an important point, so let's write that down. So note that the number p itself should not be deleted. So should not be deleted. Okay, so now we get on to the fourth step, is find the first number, find the first number that is greater than p. That's the symbol for greater than. Find the first number that is greater than p that has not been deleted. That has not been deleted. If there is no such number, if there is no such number, then the algorithm actually goes ahead and stops. So we'll say if that is the case, then the algorithm actually stops or terminates. Else what we do is let p equal the new number. So we let p equal the new number, and if that is the case, then what we do is we go ahead and repeat from stage 3. So we actually, if that's the case, if we come here, then we go back and start again from step number 3. So let's write that down. So we repeat from step 3, and then we get to the final part of the algorithm, and that is the following. That's step number 5, that when the algorithm stops, So when the algorithm actually stops, then all remaining numbers are primes. Then all remaining numbers are actually prime numbers, are primes. And that's it. You see what a simple sort of algorithm it is, and this was proposed a very, very long time ago. And what we'll do now is we will demonstrate this algorithm in a particular example, and in that example we will choose the number n to be equal to 100. Our objective here is to actually identify all prime numbers less than or equal to 100. So what we do is we will start by highlighting the smallest prime number, which is 2. Then we go ahead and identify all multiples of 2, and then we delete all the multiples of 2, but we do not delete 2. Then we find the next largest number from 2 which has not been deleted, which is 3. We highlight 3, we identify all multiples of 3, and then go ahead and delete all the multiples of 3, again leaving 3 alone. The next number is 5. We repeat the procedure. We highlight 5, identify all multiples of 5, and then delete them. Similarly, the next one turns out to be 7. Highlight 7, identify multiples of 7, and then go ahead and delete them. And if we carry on in this way, what we find that all remaining numbers turn out to be prime numbers less than or equal to 100. He was a rather accomplished person who went on to become the chief librarian at the Library of Alexandria, and in fact even has a lunar crater named after him.